Okay, our next speaker is Professor Frank Keutsch from the University of Harvard. So Frank's research combines laboratory and field experiments with instrument development to investigate fundamental mechanisms of the anthropogenic influence on atmospheric composition within the context of impacts on climate. So Frank.
Well, let me first thank the organizers for a really great conference and the opportunity to tell you about some of the work my group is doing. And I'll skip over the first slide. There's not a whole lot. One thing is that what you heard about stratospheric aerosol injection with sulfur is obviously already a future scenario. And I'm sort of going to talk about the even more future scenario in some sense. And that is trying to explore other aerosol materials to investigate this and to motivate why this could be a future thing to think about. I want to show this, which is Mount Pinatubo eruption. And really the only points here is that it put about 10 million tons of sulfur, give or take. It varies what you exactly look at the sources for this, into the stratosphere as SO2. The SO2 gets oxidized to sulfuric acid, which is very sticky. It forms droplets. These droplets or aerosols then reflect the sunlight back. And some of the things we know about sulfuric acid in the stratosphere is that it can result in ozone destruction. That's probably one of the main things one hears about as a risk of stratospheric aerosol injection. And there's a paper here that shows by year the amount of ozone on the y-axis. And you can see the green, this green and this red line are post-Pinatubo. And you can see ozone was reduced from this dark green line and the blue shading around it, which was sort of the average and variability of this before Mount Pinatubo. In the paper that I'm quoting here, there's actually an interesting statement that says before, in 1963, there was a big volcanic eruption. It probably wouldn't have resulted in ozone loss. And why is that? Is that this ozone loss comes from the chlorine from the CFCs that have gone into the stratosphere. And due to the Montreal Protocol and follows up, actually chlorine is really going down the stratosphere. So I personally actually think that by the time sulfuric acid during may occur in the future, ozone probably is not that big a problem anymore. I'm not saying we shouldn't be concerned about it, but it'll be even less in this. And remember this number, 10 megatons of sulfur. I actually think that's a fairly significant amount of injection for any perhaps realistic scenario. The thing we also know is that these particles cool down at the planet, the surface. What you're seeing here is Pinatubo occurs. In the years after that, you can see there's this temperature anomaly, which means that the temperature varies from the previous average. And you can see there's black lines, which are observations, and red lines that are the models. And there was an El Nino, so it's a little hard to really know exactly what happened. But there was a cooling of, say, about 0.5 degree Celsius that lasted for about a year. And what you're seeing here also is what was mentioned before, kind of that the aerosols stay in the atmosphere, sort of on that timeline, right? As this goes down, this has to do with the aerosols slowly coming out of the stratosphere. They're sort of going towards the poles and being deposited. The sulfuric acid is going back down to the surface again. To give you an idea of amount, these 10 million tons of sulfur turned into more sulfuric acid, but anthropogenic emissions are about 100 million tons of sulfur at the moment that are pollution that we're actually trying to get rid of. Just to get a relative amount of what we're doing with pollution compared to sort of a scale that we're talking about with stratospheric aerosol injection. This cools the surface, and that, of course, is one of the things that why we're talking about this. And you can calculate this fairly well. Another thing that happens at the same time, and this is actually for me the larger motivation to talk about materials other than sulfuric acid from a stratospheric perspective, is this. On the left-hand side, what you're seeing is the temperature in the stratosphere, which actually has been declining as the surface warms, and that is due to greenhouse gases. Right? And as you can see, there are sort of these two perturbations where suddenly temperatures in the stratosphere spike, and that is due to volcanic eruptions. The sulfuric acid that cools the surface actually heats up the stratosphere. That's one of the side effects, one of the risks that happens with this. Why should we care about the temperature in the stratosphere? This is not where we live, it's up there. Why does this matter? Well, one of the things is that in the Earth system, the entire dynamics is coupled. The stratosphere and the motion of the stratosphere doesn't happen in isolation. It's coupled to the motion of the troposphere. In the end, you can even argue it's coupled to what's happening with ocean circulation to some degree. What does it have to do with the temperature? Well, one of the, I think in the last WM ozone report, one of the key figures that had nothing to do with stratospheric aerosols or anything yet, this is what this shows is a change in age of air in the stratosphere. What does that mean? You can sort of give an average age for the air in the stratosphere. How long has it been in the stratosphere? And that has to do with how fast it circulates. If it moves through the stratosphere fast and comes back down, the average air will be small. And if it moves more slowly, the average air will be larger. And what you see here on the y-axis is the change in year per decade of stratospheric air. And when it's negative, it means that the stratosphere is speeding up, and it's beautiful. Models are extremely consistent, I would argue, pretty much. These are all kinds of model comparisons, and they say that the stratospheric circulation in a specific area, that doesn't matter too much, is speeding up significantly due to the greenhouse gases and the changes in temperature. If you look at the few observations we have that are trying to get to this number, based on looking at traces that kind of tell you how long they've been in the atmosphere, you get the same actual magnitude of, let's say, about 0.15, but the opposite sign, right? So to me, that is one of the things where I'm not saying the models are wrong, and the new ozone report says, oh, look, but the error bars are starting to overlap, and that's true. But one of the things that tells me is that perhaps we don't understand the response of stratospheric circulation to temperature changes as well as we think from the models. And I'm not saying they're wrong, but we don't know it. So to first order, it'd be kind of nice to have materials that perhaps don't destroy ozone and materials that perhaps don't affect stratospheric circulation, because it's a knob that we don't understand very well what it could be doing. Well, why does this happen that sulfuric acid actually warms up the stratosphere? This has to do with the physical properties of sulfuric acid, and it actually has to do not with sunlight, they're reflecting back sunlight, but what they're doing is they're absorbing the infrared, the heat radiation coming from the surface. What you're seeing here is what we call an infrared spectrum, so different wavelengths. It's the same thing as if you thought of different wavelengths of light in the visible, green, blue, red, whatever. This is just in the infrared, different wavelengths. And what you can see here, this tells you how many photons are coming to space at each of these wavelengths. So it's like thinking about a photo of Earth, and in some parts in some colors there's a lot of light and others not. And what you see is that where there's a lot of photons coming out here, that corresponds to a hot black body curve, 290 Kelvin, that's really the surface temperature. There are some regions where the number of photons corresponds to a hot surface, say the surface of the Sahara, for example. And then there's some regions where it's a really cold surface that you're seeing, and that's where the greenhouse gases absorb. And what you have here is this thing we call an atmospheric window, where there's fairly few absorptions of greenhouse gases, and at these colors of infrared light, light goes directly to space. And now I put my sulfuric acid there, and it actually absorbs exactly in these windows. So it is absorbing a lot of heat radiation going to space, and that results in heating of the stratosphere and perhaps unwanted effects. Why does this matter to the Arctic? Alistair just sort of explained how SAI impacts the Arctic. There's all kinds of things where stratospheric heating, which is a sort of a much more specific part that wasn't mentioned, it can affect the polar vortex stability, it can affect transport of aerosols, how efficiently it happens. It is not quite clear which direction that goes. Could it result in more cooling or less cooling? There's a lot of words that just say what I say there more explicitly, but it could have an impact, stratospheric heating, also on the Arctic, and it could have an impact more broadly on the planet of where the jet streams lie and all kinds of other effects. So the idea is look for materials that don't do this. What happens is if you put a material up there, it has a surface and it has a bulk. And the bulk tells you about radiative forcing. The interaction with light occurs more with the bulk of the material. So if we know the bulk properties, we can predict whether it's going to reflect sunlight back well, whether it absorbs radiation. The surface is what matters for interactions with the atmosphere, ozone loss. If particles are going to stick to each other when they coagulate, in large part is driven by the surface of this. All right. So what we're looking for is trying to find particles which have ideal bulk properties, so they reflect back sunlight, don't absorb sunlight, don't absorb heat radiation, and whose surface will ideally not really interact at all with things and have no impacts on, like the way ice freezes in cirrus clouds happens on the surface of particles, right? So all these things, we want to have surfaces that don't do that. The strategy is to find particles that are earth abundant. Why would you want to have earth abundant materials? And I'll give a specific example that's not really earth abundant. That is because these particles don't exist in the stratosphere. We have to understand them. But they come back down to the surface. And if you use a material there that exists in vast amounts in our atmosphere at the surface, there should be less surprises. I'm not saying there's no impacts, but there should be fewer surprises. So carbonates, if you look at what the minerals that make up the dust in the atmosphere, it's dominated by carbonates, calcium carbonate, dolomite, another carbonate. There's quartz, there's some silicates. And so trying to look at these materials partly as something one could potentially use. Carbonates, oxides, quartz, alumina. And one of the materials that we've identified as sort of a perfect material in a model is diamond. It is a prototype material as a thought experiment. It is clearly not earth abundant, all right? I'm not making that statement. But we can learn about that. All the statements that have been made about this, it's all been models that are really based largely on ideal properties that you get from a scientific catalog, and we want to know what actually happens when you do this. Just to show you the impact this has in models, if you look at SO2 injections and you look at how much you have to inject in this model per year to achieve a radiative forcing of 1 watt less per square meter on the surface, you need similar amounts, rough give or take, for the different materials, but the amount of heating you get from different materials of the stratosphere is quite different. All right, that's the main thing. And ozone, there's a very large uncertainty because it has to do with surface. I'm not going to focus on ozone. So you can get in a model different results, and if you put diamond in, it's even better, all right? One of the questions that there's lots of questions about all these things. How do these materials actually involve the stratosphere? We don't really know, they don't exist there. What I really want to focus on is that now we want to go away from these catalog materials and actually use real materials and do some lab experiments to see how they actually perform in reality. Things I don't address is cost. There's a huge question whether you can actually get them in the right size into the stratosphere at all. Lots of questions that are unopened. Here are a bunch of materials that we were looking at. We're looking at diamond from various vendors. These are commercially made diamonds that are 100 nanometer, the right size that we want to have good scattering properties. One of the things is these are insoluble. When they come back down to the surface, you can imagine they're going to stay particles. They don't go away, all right? So that's sort of, it's unreactive. There's other materials like quartz and corundum that have similar properties. And then there's a whole range of different carbonates that we're looking at that are earth abundant. Some of these are a little water soluble, some are have very low water soluble, some react a lot with HCl, which is in the stratosphere that could drive ozone loss, some do it less. So there's a whole parameter space in this. We're just starting a lot of these studies, a lot of work to be done. I just want to show the importance of actually going away from doing this in models to doing experiments. And it shows some of the fallacy I had in thinking about this. We use two different materials. This is of diamond that I'm going to focus on. These are diamonds stuck together, and down here you can see diamonds. They are really diamond. We study that they are diamond. We look at their properties. And then we thought, you know, my hypothesis to my students was these diamonds are the perfect material. They're unreactive. They don't do anything. You know, they're scatter light back. So it's like this prototype ideal material. And, you know, whether, you know, when they come back down and you want to have solid diamond dust coming down, that's a different question. It's very little, but still. But we did this experiment together with KIT in Germany, where we wanted to know, well, as these come back down, they actually could form the influence of cirrus clouds. Cirrus clouds are really quite important for climate. And my prediction was that, you know, these diamond, it's a very hydrophobic surface. That's not going to really do any ice nucleation. And I was very convinced of this. And we went to KIT, we did a study. What does this figure show you? As a function of temperature, going to low temperature, what the y-axis shows you is how much above the equilibrium for ice you have to be to start forming ice. And what you can see here is if you have to be at a high supersaturation, these things don't really like forming ice particles. If you essentially are at very low supersaturation, they're really good at forming ice particles, right? And this, what we see here is bismuth triiodide, which is generally seen as a pretty good ice nucleus, sort of as a calibration experiment. And then we put in our diamond dust. And our diamond dust is a much better ice nucleus than the bismuth triiodide. And in fact, it's one of the best ice nuclei they have ever seen in this chamber. So this was a surprise that I didn't expect. We put in diamond from another vendor. Same thing happens. In the stratosphere, I'll explain this in a second. One of the things that happens is you collide with sulfuric acid, and so they get coated. And what you start seeing there is that there's two types here, TF and AE. It doesn't matter what the difference is. One type of diamond that we bought didn't change at all when you coated it with sulfuric acid, and the other one changed from a really good ice nucleus to not a good ice nucleus. So what is the point of this slide? The point of this slide is that when we look at these alternative materials, I do think there's quite a lot of promising materials, but there's really surprises. Doing this in pure model world, I think comes with a whole lot of uncertainties that one has to address by doing experiments. Because as I said, this diamond showed that even with something that in a textbook, you look at it, really should be ideal and perfect, you start doing experiments and there can be surprises. So one of the things is that I think there is quite a lot of promise in these materials, but we do need to do a lot of work to actually try and explore what the properties are and whether the reduction in the stratospheric risk you may get from it, what are the other risks that come in on Cirrus and when it gets deposited to the ground. Thank you very much.
Is this working? Yeah, Frank, really great talk. Thank you so much. Next steps.
The next steps is we're really studying some of these carbonates, because the carbonates, one of my things is the carbonates, when they come back down to some degree, actually will be dissolving in water. And so their impact in the environment is much less. Also, we know that there's huge amounts of windblown carbonate mineral dust. So that, you know, when you think about other impacts on the environment and health and other aspects, their impacts are much better understood and generally thought of as, particles are never good to inhale, but still these are fairly environmentally benign materials, the carbonates. And there's huge amounts available as well.
I have a question and then a suggestion. The question is, the increase in the temperature of the stratosphere would cause the circulation impact you mentioned. And these things obviously are acting as heat sources. So do we have any idea of the surface temperature that they achieve under a steady state, and how surface temperature might impact the surface absorption that might impact downstream chemistry? So whether there is a trade-off between keeping them clean on the surface versus how much larger scale circulation impact they have. That's my question. The suggestion is you can try SF4 and sulfur hexafluoride plasma to functionalize your diamond nanoparticles. Maybe they will not react at all.
Right. So those are two separate questions. So I think fundamentally they're still at equilibrium with the actual surrounding air, because they're very small, and so that the temperature equilibrates very quickly. The surface functionation, I totally agree, that's something we thought about, but at the same time, you know, you're going to have OH and UV and ozone out there, and so one of the things one has to think about how that actually would survive in the environment. And I'm still, you know, diamond to me fundamentally, it's more of an example of a prototype material that in a model looks fantastic. I don't really necessarily think that is one to sort of really pursue.
Yeah, very quickly, I mean, scientifically it could be interesting, simple.
Yeah.
Like fluorinated diamond surface is extremely stable. I don't think you can destroy that very easily.
You're right, and I mean, even the normal one is fairly stable.
Yeah, but it's hydrophilic.
Yeah. Okay, let's get to the next question.
Hi, that's Steve Willis. What is the catalytic activity of the different types of material? Alumina is a well-known catalyst for all sorts of things. How do the carbonates compare to the aluminate?
That's a very good question. And Sandro is in the audience, who actually had that figure from that showed the per radiated forcing, has been doing quite a bit of, there's very little work on the specific catalytic activity with ozone of alumina. There's a little, and for none of the other materials, there's been really any studies. So we and others, including the group at ETH and others, and a group at Columbia, are starting to look at the catalytic activity of these compounds with respect to ozone in the stratosphere. So we don't know, is the simple answer.
Hi, Frank. In the SPICE project, titanium dioxide seemed to be quite a promising thing, but you seem to have not put that on your list.
I would argue titanium dioxide is pathological in that it is a photocatalyst. So what are the two things why that makes it, in my opinion, and I don't want to be rude, but the idea is it's a photocatalyst. That means by definition it actually absorbs sunlight. That, by definition, that results in significant stratospheric heating. And as I've pointed out, actually, the stratospheric heating, to me, messing with atmospheric dynamics I'm just very wary of. The other one, as it's a photocatalyst, it actually does catalytic chemistry, and who knows what catalytic chemistry it will do in the stratosphere. So I think it's a great material down here. We use it in sunscreen and all these things, but there's not that much short UV here. So I just think those two things, that it's a photocatalyst, absorption, and chemistry, to me just make it a really not a great choice for the stratosphere.
Hi, thank you for a great talk. I actually have a question that sort of falls on what you was asking about surface properties. We would like for, say, a diamond or anything to be passivated, but then we worry that it would have carbon-oxygen tails or OH tails. Nanoaerosolization of any substance is a highly energetic process. Does that mean that those kinds of impurities and functional bits that are created by that high energy process are inevitable, regardless of our material?
So you're saying whether the dispersion process will affect the surface? They may. I think what matters in the end, actually, one of the problems in these studies that has happened is people have looked at these pure materials in a lab. What you actually need to know, they're up there for a year. What really matters, that's actually the most irrelevant part, because that's right when they're in the stratosphere. What matters is what happens to those surfaces after a week, a few months, a year. And that hasn't been studied. So one of the things that's going to happen, it's going to get coated with sulfuric acid, right? And so in that sense, it could be that if it doesn't react with sulfuric acid, that actually it doesn't really matter was on the surface of the material, because now it's coated. But the question of how much coating is on there, there's also the question, depending how much you put in, you could get it from a scenario where everything kind of gets coated to where there's actually not enough sulfuric acid around to coat it. So there's a whole parameter space in there where what really matters, and what happens to the surfaces with UV, ozone, OH. I've discovered one molecule that in stratospheric models plays absolutely no role, that could play a role for the carbonates. And it just sort of shows you that when you put something new in the system, you've got to be very careful and think about, what do these surfaces evolve to? I think that's much more important than the initial surface. But that's just sort of my personal view.
Okay, let's thank Frank.